You probably will. We are officially beginning now. Okay, so before the break, we discussed about upper confidence bound, and we basically discussed the strategy that you have some estimates and you also have confidence bound for these estimates. Okay, now these confidence bounds might vary. Like for example, if you're highly confident, the gap is too small. If you're less confident, the gap is too wide, and the goal is to really have very high confidence for every estimate. So now there are two reasons why you want to explore an action. Like one, it is very close to the optimality, which means you have to be more confident about its estimate, or two, like it is just highly uncertain estimate, so you want to make it more certain. Okay, now how to implement this, right? Like, so here is a simple way of doing that. So AT is given by argmax of A, okay? So QT of A plus C times square root of ln T by NT of A, okay? Now this extra term that I have here, okay? But by the way, thanks for people telling me that there was no audio, otherwise we would have lost the recording of this lecture. Okay, so also for people in class, like, so please remind me once in a while when we start, if I have to start recording, start audio and so on. Okay, so now what is this extra term, right? So intuitively, okay, first of all, T is the time step and NT is the number of times I have taken the action. Okay, now intuitively, this second term is a measure of uncertainty, okay, or the variance of my estimate in this action value. Okay, now you can see that as I see this action, as I take this action more and more, NT value is going to increase, right? Which means it's in the denominator, so this term is going to get smaller, right? So now this term is kind of like an upper bound for my estimate, okay? Now, as I see the action more and more, NT of A is going to shrink, which means the second term is going to shrink, and eventually, like if I have taken this NT of A infinite times, then what I am left with is just QT of A, which is the estimate, right? Now, every time I take an action which is not action A, okay, so then the numerator term, ln T, increases, which means if I take other actions too much, then this numerator term encourages me or reminds me that probably I should take this action once again, okay? Because as the numerator increases, the uncertainty again increases, okay? So if you don't take an action too much for too much time, then the numerator term reminds you that you should take this action again, okay? However, like we don't want this to be as significant as NT of A, so that's why we have a logarithm there. Like, so you put a ln T so that this uncertainty reduces linearly. However, uncertainty increases logarithmically. Yeah, question?
I don't completely understand the equation because you said that problem we are dealing with is a stationary one, right? So when we are taking other actions, why are we actually increasing the uncertainty?
Well, it is just to make sure that like you don't stop taking this action, even in stationary, until you figure out what is the optimal action. Like you have to try taking all the actions, right? But there is, your point is right. So that's why we have a logarithm in the top. So eventually, what will happen if you continue forever is the denominator is going to dominate. So like you will stop taking that action once you are highly certain. So it's not exactly handling non-stationarity because this is still going to saturate. So it's going to saturate because you have ln T in the top and like just T in the numerator. There was another question. Yeah.
I'm not sure what it does. This term, does it add? Does it make it more? I'm not sure.
So can you elaborate?
Well, it's supposed to add a term, a measure of uncertainty. So it adds, yeah, I'm not sure.
Okay, so what exactly it is doing, right? So, well, if we have to derive UCB, probably that is like a couple of hours of lecture, so we are not going to do that. So that's why I gave you the algorithm directly, okay? Sometimes I'll give you the algorithm directly. Sometimes we will derive it. Like we are going to do a mix and match in this course. So just to make sure you get the feeling of both. But in this case, like I think the confusion is like how is this measuring uncertainty and what is it doing, right? So now of course there are many ways to measure uncertainty. This is just one of the many ways. This is probably the simplest way because you are measuring uncertainty just by the frequency count, right? Like, so just by the frequency or the count of the number of times you see the place. So this basically makes an assumption that if you visit an action very frequently, your uncertainty reduces. If you don't visit it like for a long time, your uncertainty slightly increases. Okay. Now this C term is is a constant. Okay. So C greater than 0, it controls the degree of exploration. Okay. So now let's see how this UCB algorithm works when compared to epsilon greedy. Okay. Now remember that in this case there is no epsilon. Like so, you have a different. In epsilon greedy, epsilon is the hyperparameter, right? Like you have to pick the epsilon. But in UCB, you have to pick C. C value is the hyperparameter here. Okay. Now let's see how this algorithm. Okay, I don't have the UCB. Okay. Okay, so it looks like I don't have the. It looks like I don't have the UCB results here. So let's actually go to the notes. No. Yep. Okay. But there seems to be a lot of issues with recording. I don't know why. Okay, it might be because I moved things too fast. Just give me a minute. Okay, so is the recording fine for people in the Zoom? Like the video? No, I think I moved things too much. Something happened. Let's see how to fix it. Okay, people say it usually comes back on its own. Okay, it came back. Okay, so we are still not, we haven't mastered like remote lectures yet. Okay, so here you can see how UCB performs when compared to epsilon greedy. Okay, so epsilon greedy with epsilon is equal to 0.1 versus UCB with C is equal to 2. Okay, I should not annotate the lecture notes. Okay, so you can see that UCB is doing better than epsilon greedy. Okay, so again, you're going to implement UCB in your assignments, so you will get a first-hand experience of how it works. Okay, now let's talk about non-stationarity. So there was a question like, so how does this deal with non-stationarity? So, well, the truth is this doesn't deal with non-stationarity. It's actually very difficult to incorporate non-stationarity into UCB algorithms, but I'm sure there might be some work just trying to do that. It is just that it is not trivial. And the other issue here is it is also very difficult. It also becomes very difficult when you have a very large action space. Okay, so like if you have 10 actions, you can count the number of times you are visiting the actions. What if you have millions of actions? Okay, now you might not visit all the actions that frequently so that your estimates become better. Okay, now you might think like, how can we have a bandit problem with million actions? But when you go to the full reinforcement learning setting, where we are going to use these ideas of exploration that we develop in bandits, then you would appreciate epsilon greedy, because it is very easy to extend epsilon greedy to full reinforcement learning. However, it is very difficult to extend UCB. It's not impossible, but it is very difficult because in a reinforcement learning problem, you will typically have millions of states. Okay, so like in a very complex reinforcement learning problem. So in that case, like state visitation or the frequency count are too low for all the states. Like So these kind of estimates doesn't make that much sense. But that much sense. Okay. Okay. So now we have seen epsilon greedy, right? And we have also seen UCB, or upper confidence bound, right? So now we are going. So these are both based on estimating values of actions, right? So they are both based on action value estimation. Okay. So now I'm going to introduce a slightly, or not slightly, like a very different way of approaching this problem, which doesn't include action value estimation. Okay. So we are going to find the best arm just based on preferences. Like, I don't estimate the action values directly. I just want to learn like what is the which arm has maximum probability for being optimal action. Okay, so there's a small difference here. Like, so like if you have the value estimate, of course you can compute the probability, but the question is, can we directly compute the probability instead of worrying too much about value estimates? Okay, so that's a second class of algorithms. Okay, so now, so we are going to see one example of such algorithm, which is basically gradient bandit. Okay, so the idea here is for every action A, I'm going to associate HT of A, which is basically some numerical preference, okay, for choosing action A. Okay, if this HT is high, then it means I'm going to pick this action more often. If it is low, I'm going to pick it less often. Okay. Now, this is not my value estimate. Okay. This is some arbitrary number. If this number is high, I'm going to, like, HT is not equal to Q. Okay. Let's just be clear on that. So HT is just some number. The higher the number, more probable I'm going to pick this action. The lower the number, less probability, like with less probability I'll pick that action. Okay. Now, once I have these preference numbers, then I can set up a probability distribution over actions. Okay. So how am I going to do that? You can do a simple softmax over these action preferences. So the probability of picking action A is given by e power HT of A divided by summation over B is equal to 1 to K e power HT of B. Okay. I will answer the question in the chat after finishing this. Okay. So now, given a bunch of HTs, the probability is defined using this equation. So let us just call this probability as pi t of A, the probability of choosing action A at time t. Okay. Now, this form of the probability distribution, right? Like, so, like this is called Gibbs or Boltzmann distribution. Okay. So if you have already done machine learning, so this is just a simple softmax function, right? Okay. Now, pi t of A is basically the probability of taking action A. Okay. So now, so why did I say that HT is not the same as QT? Okay. Because I can just add arbitrary constant to all the HTs. Like, for example, I just add plus 10,000 to all my HTs. Okay. The probability distribution doesn't change. Okay, so I can translate like or move the numbers like in different directions, and the probability distribution doesn't change. Okay. Also initially, okay, so H1 of action is going to be 0 for all actions. Okay. Now this initial bias is different from the Q value estimate bias, right? Like, because in Q values you can actually go off by having Q1 is equal to 0. However, in the preferences, it's kind of true because initially I don't have any preference, so everything is set to 0. So e power 0 is 1. So all actions have equal probability. and slowly I increase and decrease the probabilities, okay? So how do I increase and decrease the probabilities? That is what the algorithm is, okay? But before that, I'll take some questions. So concerning the notation, do we call Q the value or action value? So that's a good question. So Qs are basically value estimates of the actions, right? Like, so they are action values. For now, they are same. Okay, the question is value and action value same? For now, they are same because we haven't seen the notion of states yet. So once we see the notion of states, then we will have two types of values, state values and action values, okay? So for now, they are same, but not always. Okay, yeah?
Can you please explain what is B in the equation?
What?
What is B in the equation?
B? Oh, so it's just index for all the actions. So you have k actions, right?
Okay.
So it's just divided by e power ht for all, sum of e power ht for all the actions. Okay, I think the main question here is how to learn the preferences, right? So just like what I did for UCB, like I'm going to give you the algorithm first, but in this case, like we are actually going to like see how we came up with this update equation as well. Okay, so this is going to be a slightly more mathematical section of the lecture, but it is very useful for the future lectures. Okay, first the algorithm. Okay, so the idea is very simple. So let me write the update rule first. So ht plus 1 of at is going to be ht of at. As you can see, new estimate is equal to old estimate plus some alpha times some target, like the error, right? So I'm going to call, let me first write it and then I'll explain it, okay? Okay, now, first of all, alpha here is the step size. Step size, okay? So alpha is something greater than 0, okay? And I have this new term introduced here, RT bar, right? So now this RT bar is basically the average of all the rewards, not just this action, but all the rewards I have seen so far up to T. Okay, so now let's try to understand how this algorithm works. Okay, so here you can see that, let's say average of all my previous rewards is 5. Okay, I take action 80 and I get a reward of 7. Okay, now what does that mean? It means it's on an average a good action to take, right? So because it is higher than the average. So 7 minus 5 is 2. So it's positive, which means that this is actually a good action to take, which means I should increase the preference for this action. Okay, now how am I going to do that? So as usual, like we're going to have a step size just to be conservative. So step size time RT minus RT bar, which means it could be positive or negative. If it is positive, then this 1 minus phi t is the probability of not taking this action. Okay, you take that probability and you bring sum of that to probability of taking that action. Okay, so however, if let's say RT is 2, average is 5, RT is 2, what does that mean? This is actually not a good action to take. Now, if you look at the second term, 2 minus 5 is minus 3. So you are reducing the preference for this action then. So the probability of not taking that action is going to increase. Okay? Do you understand the algorithm? Now, it is not just enough I increase the probability of taking this action. Okay? I am also going to decrease the probability of taking other actions if I think this is the good action. Okay? So how am I going to do that? So I'm just going to have a similar update equation. Okay, so ht plus 1 of a for all the actions which are not at. Okay, so for them I'm going to do ht of a plus alpha times rt minus rt bar times pi t of A. Okay, so if the reward is positive, then I will reduce the probability of taking that action for other actions. Okay, this is for A not equal to A2. Okay, and the other way around. Okay, is this idea clear? Yeah.
Last contribution, the last term, why you're using the last term?
Oh, the last term.
Yes, 1 minus pi t.
Oh, so that is true. So essentially what we are trying to do here is like, we want to increase the preference, which means decreasing the probability of taking that action. There are a lot of hands, so.
If we want to decrease the preference for the other actions, shouldn't RT bar and RT be switched in the second equation?
Oh. Well, that's why no, so that is taken care of by the pi t term. So instead of 1 minus pi t, we have pi t there. I know this is a little bit hard to take in, so.
It's the same question. Like it's if the reward that you are receiving is higher, then this is actually increasing the preference of other actions.
Okay, is my update equation wrong?
Because pi t is still positive, right? So.
Okay, I think it should be a minus in the front. You might be right. Just give me 1 second. Okay, so maybe that's my mistake in the notes. Just give me 1 second. Yes, it's my mistake. So this should be minus. Okay, so you're decreasing. Sorry. Does that? Okay, I think the notes is wrong, so I should fix it. Well, I would have written it at 1 a.m. Does that fix all the doubts? There are a couple of other hand raisers. Yep.
Mine was a much dumber question. What's large AT? It's a vector of all the actions
Okay.
times that t?
No, I think probably I did not explain my notations clear. So AT is basically the action that you took at time t. Okay.
Just one action.
One action.
Okay.
Now, small a is all the actions that you did not take at time t. If you have 10 actions and you took the second action, then AT is 2.
Okay.
So you do the first update for the second action. You do the second update for rest of the actions.
Thank you.
Okay. So now let's see how this algorithm works. Maybe this time I have the graph. Yeah. Okay. So here you can see the same 10-armed bandit setting. Okay. But I'm going to. I think I'm increasing the reward, like the mean of the reward from. It was initially 0 or 1. I think it was 0 mean, right? So instead of 0, I'm going to consider mean to be +4 or +5, some larger value. Okay. So when you have a positive mean for all the actions, it's a bit of a hard problem because everything is positive initially, right? So now in this case we are seeing 2 versions of gradient bandit algorithm. Okay. So one with baseline and the other one without baseline. Okay. So what do I mean? So the without baseline algorithm actually doesn't include RT bar. It just has RT. Okay. So if I get a positive reward, I increase. If I get a negative reward, I decrease. Okay. Now you see this is a bad idea, right? So what if all the actions have positive rewards? then you're increasing the probability of all the actions, right? Like for example, let's say there are 5 actions and the rewards are 1, 2, 3, 4, 5. Okay. Now, if you are just using RT, then you are increasing the probability for all the actions. However, we should be increasing the probabilities for this actions and decrease the probability for this actions because these are too low, these are too high, right? So this simple trick of adding a baseline RT bar, right? Like the simple trick of adding RT bar, the baseline, actually helps us to fix this issue. Okay. Now you can see that in action in this figure. Like so, you can see that if you don't use baseline, your performance is really bad. However, when you use baseline, like you get a good performance. Okay. Any questions? Okay, I think I should check the. Okay, any other questions? Okay, so now we are going to. Okay, how are we doing HT in Bandit? So how are we doing HT in Bandit? What do you mean? So I think we initially set all the HTs to 0, and then we are just going to use these update equation. Oh, the question is about hyperparameter tuning. The hyperparameter here is alpha. Okay, so you have to fix an alpha. So I think we did not discuss about how to tune these hyperparameters for any of the algorithms, like how to tune epsilon, how to tune C in upper confidence bound, or how to tune alpha in gradient bandit, right? Like so, probably we will not touch the topic in this course. Like like we'll discuss more about it in the machine learning course. But just to give you a quick idea, right? Like so, it really depends on the situation. Like so, for example, I give you access to this bandit algorithm again and again, like a lot of times. Then you can try different alphas and pick the best alpha, right? However, the most realistic setting is you don't have a lot of chances to interact. Like so, I put you in the real world, you have to act, and every action counts. So now you cannot try the same thing again and again, right? Like so in such cases, you cannot do hyperparameter tuning. So either you fix a hyperparameter, or you come up with a heuristic to change this hyperparameter over time and so on. So, but for the purpose of this discussion, I will not worry too much about it. Okay, so now, okay, sorry. So now let's actually, okay, now, yep, question?
I assume that to choose the next AT, we just sample from the distribution. Just sample.
To choose?
Yeah, choose AT.
Oh, yeah, that's a good question. Yeah. Sorry. So I did not tell you how to use these estimates, right? Like so, to use these estimates, you just sample from the softmax, which means you are also doing a little bit of exploration. Okay, yeah.
They did like the initial optimistic initial values, like you guess the for the.
No, this is not like initial optimistic values because you are setting equal preferences in the beginning.
Yeah, but for the baseline, you need to for the average. Yeah, if you put 0, then we see that the same problem occurs.
Oh, that's a good point. So what is the initial baseline that might have some effect? But since this is average of all the rewards, like it's going to get better over time. So it should be fine. Okay, so now for this gradient bandit algorithm, okay, so we are going to see that this is actually a much more principled approach than the heuristic that I explained today. Okay, so now we are going to, okay, the screen thing is happening again. Okay, so we're going to see the bandit gradient algorithm as stochastic gradient ascent. Okay. Now, so maybe I will wait for the screen to resolve by itself. Is there any other questions? Yeah?
The pi t of A is the same thing as the Qn? Because Qn was supposed to.
Oh, no. So pi and q are different things, okay? So q is my action value estimate. Pi is just the probability of taking action A. Okay. As I said before, like pi is just based on preferences. It is not based on the action values directly. Okay, screen resolved. Okay, so now let's say I have my performance measure, which is basically the expected reward that I would get, and I want to maximize my expected reward. Okay, one way to do that is by directly computing how this expected reward changes with respect to my actions. Okay, and do a gradient ascent on this. Okay, so the exact gradient ascent is basically how do I update HT of A? So HT plus 1 of A is equal to HT of A plus alpha times my gradient differentiation with respect to the expected improvements. Okay, so dou E of RT divided by dou HT of A. Okay, so where my performance P, okay, maybe let's not name it as P. Performance is given by expected value of RT, okay, which is basically summation over all possible actions, okay. So pi T of X, the probability of taking that action multiplied by the return from that action, okay. Now this is just an expected return, okay. So expectation is with respect to the probability of taking these actions. Is this clear? Okay. Now, this is kind of an ideal algorithm because what this algorithm is doing is it tries every action, see the rate of change in my expected improvements, okay, and move towards actions which has more expected improvements in the return, right? However, this is an impractical algorithm. Why? So why is this an impractical algorithm? Yeah?
You don't know Q star.
You don't know Q star, right? Like, so if you know Q star, then you can actually compute this gradient and do this repeated process of gradient ascent. You're going to reach optimal policy, okay? Like, or like, which is the optimal action to take, right? Like, so, however, we don't have access to Q star, okay? So what I'm going to show now is whatever we did with the heuristic version of gradient bandit algorithm is a stochastic approximation for this ideal update equation, okay? So now to do that, we should first consider dou E of RT divided by dou HT of A. Okay, so now this is basically dou by dou HT of A. I'm going to substitute my return here, expected return, so which is basically summation over X, pi T of X, Q star of X, right? Now, this is summation over, I'm just going to move the differentiation inside. So summation over X, Q star of X, which doesn't have anything to do with the preferences, dou by dou HT of A of pi T of X. Okay, it's all good. Now, I'm going to introduce baseline now. Okay, so this is, I'm going to add an extra thing here. So this is equivalent to Q star of X minus BT times dou pi T of X by dou HT of A. Okay, where BT is some baseline, okay, that does not depend on X. If it is dependent on X, then like I think some conditions don't satisfy. So like BT should be some scalar which doesn't depend on X. Okay. Now, is it a right thing to just directly add minus BT here? And does the equality still hold? How can I add a minus BT with equality? Sorry?
The average would be 0.
Sorry, what?
If the average over x is 0, or
Yes. So in this case, you can easily convince yourself that summation over x dou pi t of x by dou ht of a is actually equal to 0. Why? Because if you increase the probability for one action, since it is a valid probability distribution, all the other actions will have equivalent decrease, right? Like, so the sum of the probabilities is always 1. So when you differentiate the probability with respect to different preferences, like, so this difference, like this gradient is always going to sum to zero, okay? So BT times summation of this term, the whole thing becomes 0. So it's perfectly fine if I just keep it like this, okay? Now, let me rewrite this so that we can move from there. So dou E of RT divided by dou HT of A is equal to summation over X. This is what we have written, right? So Q star of X minus BT dou pi t of X by dou HT of A, right? I'm just rewriting it here, okay? So now I'm going to do multiply and divide by pi t of X, which is totally allowed. So I'm going to do pi t of X multiplied by Q star of X minus BT dou pi t of X by dou HT of A, the whole thing divided by pi t of X. Okay, so now you can see that this is actually an expectation, right? Summation over all possible X, probability of X multiplied by some term, right? So this is actually an expectation. So this is expected value of, okay, Q star of X minus BT dou pi t of the action AT divided by dou HT of A divided by pi t of AT. Okay. Now, how many of you are not comfortable with this transformation? So this is basic expectation. So if you have not, like if you don't understand why I move, how I move from here to here, you should attend the probability review tutorial this Tuesday, okay? So what I have done here is really using the definition of expectation. Okay, so now we are going to do some stochastic approximations and see how that becomes the gradient bandit algorithm, okay? So what I'm going to do here is I'm going to approximate Q star of X with RT. And I'm going to consider BT to be RT bar, okay? Now, the rest of the things stays as such. Okay. Now, RT is a stochastic approximation for Q star of X because what is the expected value of RT? RT is a sample average, right? Like just the reward that I received at this time step. But what would be the expectation of that? It's just Q star, right? So basically, note, expected value of RT given AT is basically Q star of AT. Okay, so this is a kind of stochastic approximation of Q star. Okay, so now we have this update equation. Okay, so the only thing that is left out here is this dou pi t by dou ht. Okay, let us do that. So dou pi t of X divided by dou ht of A, which is basically dou by dou ht of A times pi t of X, right? And we know the actual equation for pi t, right? So it's basically dou by dou ht of A. Okay, I hope the pencil lasts for 5 more minutes. E power ht of X divided by summation over y is equal to 1 to k e power ht of Y. Okay, now this is going to be a boring calculation. So I want to differentiate something which is u by v. So what is differentiation of u by v? calculus. So what is differentiation of u by v?
Like maybe u into derivative of v minus v into derivative of u.
Isn't it v du minus u dv by v square? Right? So you're differentiating u by v, right? So it's v du minus u dv by v square. So I'm just going to blindly apply this here. So it's v, which is the denominator, okay, du, so dou e power ht of x divided by dou ht of a, minus u and dv, so dou by dou ht of a of summation over y is equal to 1 to k e power ht of y, divided by v square, summation over y is equal to 1 to k e power ht of y, the whole square. Okay, now this term, right, dou e of ht of x by dou e of ht of a. So now that is going to be e power ht of x whenever a is equal to x. Okay, so it's, I'm going to put an indicator here, a is equal to x e power ht of x. The summation term rise as such, e power ht of y, okay, minus e power ht of x, okay. I differentiate this summation with respect to e power, with respect to ht of a. So just for that action, you're going to get same e power x. For all the other actions, you're going to get 0, right? So now this summation disappears. It becomes e power ht of a, okay, divided by summation over y is equal to 1 to k e power ht of y, the whole square. Okay, so we are almost there. So now I'm just going to divide the terms. So 1a is equal to x e power ht of x divided by summation over y is equal to 1 to k e power ht of y. Okay, I cancelled one term, minus e power ht of x e power ht of a divided by summation over y is equal to 1 to k e power ht of y, the whole square. Okay, so now let me take this. Okay, so I'm going to put it here. Okay, and you can see that, can someone tell me what is this? It's just probability of taking action x, right? So this becomes 1 over, like, indicator function for a is equal to x, pi t of x minus, so what about these terms? So pi t of x multiplied by pi t of a, right? So my dou pi t of x divided by pi, like dou ht of a, has a nice form, which is pi t of x times indicator function minus pi t of a. Okay, now I'm going to substitute this in my previous one. So I'll move very slowly so that the screen doesn't disappear. Okay, so we are going to take this particular thing, copy, slowly. Okay, we're going to take this particular thing and I'm going to write it as expected value of RT minus RT bar. Okay, and I'm going to put this term here. Okay, so it becomes pi t of AT times indicator A is equal to AT minus pi t of A divided by pi t of AT. Okay, so I see there was some question in the chat about me mixing x and AT. So I think it's a bad notation which I directly borrowed from the book. Probably I'll clean it up later. Like, just don't worry about switching x and AT once in a while. So these two things cancel. Okay, so now what we are left with is actually expected value of RT minus RT bar. Okay, 1 A is equal to AT minus pi t of A. Okay, now this is an expected term, right? Like if I take a stochastic approximation of this term, then I get ht plus 1 of A is equal to ht of A plus alpha times stochastic approximation of this. So I'm just going to take RT minus RT bar times indicator A is equal to AT minus pi t of A, okay, for all A. Okay, so now you can see that this is exactly the gradient bandit algorithm, right? So now you can see that for the action capital AT, right? Now this indicator is going to be 1. So you will have 1 minus pi t, which is exactly same as the previous equation that we had. Now for all other actions, this indicator function is going to be 0, which means the minus comes to the middle. So it's minus alpha times. Okay, so what I have essentially proved at the cost of delaying the break is the gradient bandit algorithm that we have seen, like, can be derived as a stochastic approximation of the true expected gradient that one would get if you have access to Q star. Okay, now this is a very interesting result because we have a very clever approximation for like dealing with Q star even when you don't have access to Q star. Okay, so we will stop here. So since I took more time, so we will take a 10-minute break and start at 11:40.